Hey, what's going on, guys? Let's do this problem right here. The question is asking to find the work, Q, heat, and the delta G change in internal energy. And they are saying they are adding heat to the system and the volume is constant. So if the volume is constant, this is an isochoric process or isovolumetric process. It means volume is constant, right? So let's draw a PV diagram for this one and see what we can find. So PV diagram, since volume is constant, whatever the volume it is, it's going to straight like up like this, right? Because volume is going to be same. So let's say this is V, right? V, and we know the initial pressure is given right here, that's 1 atm. So here we are going to have 1 atm, and then here we are going to have 3 atm. So let's see what we can find out from this information. So whenever we have constant volume, the work is always zero. In any isochoric process, any volume constant process, or if you see a diagram that has vertical line, in PVQ diagram vertical line, that's work is always zero. So that answers the first question. So let's say this is A, B, C. For answer A, the work is going to be equal to 0. So if work is equal to 0, let's see how we can find delta G and Q. So we know that delta G is equal to Q minus W. This is a generic equation. So here if the work is 0, we know delta G is going to be equal to Q, right? Equal to Q. So if we solve one of these things, we can answer other one too, because both of them are going to be same answer. And since they are adding heat to the system, we expect a positive answer, because whenever we add heat to the system, it's positive. Whenever system loses heat, it's negative. So here it's going to be positive. And we know that to find since we have this is constant volume, isochoric process, Q is going to be equal to NCV delta T. If it's an isobaric process, for example, if the pressure is constant, we use NCP delta T. And they are saying this is an diatomic gas, right? For a diatomic gas, Cv is going to be equal to 3 by 2 R. So let's plug these values and see what we get. But before we do that, let's see we have everything. Do we have the mole? Yes, we have. And do we have R? That's a gas constant. We already know that. And initial temperature and final temperature. We have initial temperature, but we don't have the final temperature. So we have to find that one. Right? To find that one, first of all, if we use PV is equal to nRT, PV is equal to nRT, we don't know the volume either, right? We don't know the volume. So in order to find the final temperature, we have to know the volume. So let's find the volume first. Let's take the initial condition. Because if I calculate volume for initial condition, the volume is going to be same for the final condition too, because volume is constant, right? So let's calculate volume for initial condition and see what we get. So here we are going to use PV is equal to nRT. So we are taking initial condition P0, V0, T0, right? So V0 is going to be equal to nR T0 over P0, right? So here we have the mole right here that's provided, 5 mole times the gas constant, that's going to be 8.315 joules per mole Kelvin, and initial temperature it's provided, it's 293 Kelvin divided by the pressure, initial pressure, that is 1 atm, right? We have to convert this one into Newton per meter square. To convert that one, we can simply multiply this one by 101,300. So this one is 101,300 Newton per meter square. And if you calculate this value, you will get 0.12 meter cube, right? So now we found out the initial volume. So this is going to be equal to final volume too, because volume is constant. So V0 is equal to Vf. Now if we take the final condition, we can calculate the final temperature, right? So let's take all of the final condition. So let's say this is P final. P final is equal to N or T final. T final is the thing we are trying to find. So T final is going to be equal to P final V final over NR. So here we have P final, that's 3 atm. To convert this one into Newton per meter square, we have to multiply this one by 101 300. So this is going to be multiple. Let's use a different calculator. Yeah. So 3 times 101 300 Newton per meter square multiply by V final, that is going to be same as initial because volume is constant, right? So that's going to be 0.12 meter cube divided by N, that is 5 mole, times R, that's going to be 8.315 joule per mole Kelvin. 8.315 joule per mole Kelvin, right? So you may wonder how did this joule and these values are going to cancel. If you notice that Newton meter square times meter cube is going to give us Newton meter. Newton meter is equal to joule. So that's going to cancel with this joule, and finally we will end up with Kelvin. And if you calculate this value, that's going to give you 879 Kelvin. And you always have to make sure whether this value is correct. So this is going from 1 atm to 3 atm. So this means this is going in this direction. So for a PV diagram, the heat's direction is going to be always like this. So increasing in this direction. So if it's opposite, it's going to be decreasing. So since this is increasing, the final should be higher than the initial, right? So here we got 879 and initial is 293. So this is correct. So from this one we can make sure. Now we can go ahead and use this formula to find the Q value. If we find Q, that's going to be equal to delta U because we know that work is 0. So if we apply 0, both of them are going to be same. So let's plug all these values and calculate this Q. Q is equal to NCV delta T. N is going to be 5 mole, so 5 mole right here. CV is going to be 2 by 5 for a diatomic gas. For a monoatomic, 3 by 2. For a diatomic, it's 2 by 5, right? So 2 by 5, is it? Yeah, it's for a monoatomic it's 3 by 2. It's for a diatomic it's 5 by 2. So here we have to just 5 by 2. Right, here we have to use 5 by 2, and for a triatomic we have to use 7 by 2. So it goes like that. So let's apply this one. 5 by 2 times R, that is 8.315 joules per mole Kelvin, times the temperature change, that's going to be 8 final minus initial, that's going to be 879 minus 879 Kelvin minus 293 Kelvin. And if you calculate this one, that's going to give you 60,707, right? So this will give you 60,707 joule, right? If you know the Q, that's going to be equal to delta U, because we know that work is 0, this is 0, delta U is equal to Q, so this is equal to delta U. So now we have found out work, that is 0, Q and delta U are same, both of them are calculated, and that's how we do this kind of problems. I hope you guys find this video helpful. See you next time.